Credit card fraud is a relentless enemy, constantly evolving and hiding in plain sight within mountains of legitimate transactions. In this video, we will explore how we can use the isolation forest algorithm to pinpoint and detect those elusive, fraudulent activities using a Kaggle dataset on credit card fraud detection. But firstly, what is the isolation forest algorithm? It is an algorithm that attempts to isolate observations by randomly selecting a feature and then randomly selecting a split value between the maximum and minimum values of the selected feature. Random partitioning produces noticeably shorter paths for anomalies. Hence, when a forest of random trees collectively produce shorter path lengths for particular samples, they are highly likely to be anomalies. Sounds complicated? Maybe a little. Let's try to explain it using an example. Imagine you have a big box of toys, and most of them are pretty normal: cars, dolls, blocks. But then, there's one toy that's really weird and doesn't fit it at all, like a rubber chicken in a box of Legos. An isolation forest is like a super fast way to find that weird toy, which we call an anomaly or outlier in the box. Here's how it works. Imagine we randomly pick a toy from the box and try to put it in its own separate little bag as quickly as possible. For normal toys like a car, we might have to make a lot of decisions to get it alone. For example, first we separate the things with wheels from the things without wheels. Then, among the wheeled toys, we separate the red ones from the blue ones, and so on, until finally the car is in its own bag. It took many steps. But for a really weird toy like the rubber chicken, it's much easier to separate it. Maybe the first thing we do is separate the squishy toys from the hard toys, and bam! The rubber chicken is already in its own bag. It only took one step. Isolation forest does this many times with different random separations. If a toy is usually separated very quickly in just a few steps, it's probably one of the weird ones, an anomaly. If it usually takes many steps to separate a toy, it's probably a normal toy. So isolation forest is a clever way for computers to quickly find the things in a big pile of data that are unusual and don't fit in with the rest. It does this by seeing how easy it is to isolate them by randomly splitting the data. The easier and faster it is to isolate something, the more likely it's an anomaly. Now that we have a better understanding of what isolation forest is, let's get started. As usual, we will be coding using Google Colab. Firstly, we will be importing the libraries that we will be using in this notebook. Next, let us download the dataset from the Kaggle API. The data is by the machine learning group, and more details can be found in the description box. It contains transactions made by credit cards in September 2013 by European cardholders. After the data is downloaded, we can proceed to inspect it. Let's start by inspecting the column names. There are only 3 readable variables: time, amount, and class. The rest are just prefixed with V and suffix with numbers 1 through to 28. It turns out that the variables V1 to V28 are principal components obtained through PCA. Due to confidentiality issues, the original features and information have been anonymized. Time refers to the number of seconds elapsed between this transaction and the first transaction in the dataset. Amount is the transaction amount, assumed to be in the same currency. Class is the label of the data, 0 for genuine transaction and 1 for fraudulent transaction. Looking at the count of labels, it is clear that we are dealing with a highly imbalanced dataset. There are only 492 fraudulent transactions compared to 284,000 genuine transactions. The fraudulent transactions only make up 0.17% of the total number of transactions in the dataset. This is a good reflection of real-world data, and oftentimes we will see this significant imbalance. Moving on, we will check to see if there are any null or missing values in the dataset. Seems like this worry is unfounded as there is no missing data. Then, let's move on to an overview of the data distribution. As expected, time and amount are the raw data provided, while the principal components seem to have been pre-processed and scaled accordingly. As such, we will not be applying further preprocessing to the data. Next, I will create 2 separate data frames, each containing the data with distinct labels. We will use these two data frames to plot histograms and visualize the distributions of the data. I will not be showing all the histograms here as there are too many, but I will highlight a few histogram plots which I find interesting. From what I have observed, it seems that features V11 and V14 are potentially good indicators of fraudulent transactions. Comparing the distributions between genuine and fraudulent, there is only a slight overlap of distributions. The genuine transactions for V11 are clustered around the zero value, while the fraudulent transactions have a slight positively skewed tail. For V14, similarly, the genuine transactions are clustered around the zero value, while the fraudulent transactions have a negatively skewed tail. Another interesting observation was that the majority of fraudulent transactions are less than 500. This is surprising to me, as I would have imagined the fraudulent transactions to be of a higher amount. This could be due to fraudsters testing the validity of the credit cards through small amounts, or it could be fraudsters doing smaller quantum of transactions to avoid detection. Now we are ready to train the model. We will first prepare the data input. For the first model, we will train it using only the principal components and drop the rest. Next, we will instantiate the model. The model has several hyperparameters, so I will be setting values for some of them. N estimators is the number of base estimators. I set a high number for max samples to maximize the sampling size. The contamination size is set to the percentage of anomalous labels out of the entire dataset. Random state is just to ensure reproducible results each time the model is trained, else the feature selection and value split will be different each time. Then, we will fit and predict. Looking at the classification report, we can see the precision, recall, and harmonic F1 score of the model. At a glance, it seems to be good, with an F1 score of 0.36. But it needs to have comparison models, else there is no relative comparison to determine if it is a good model. Another thing to note is that the predicted labels are -1 and 1, as that is the mode of isolation forest output labels. -1 will be predicted fraud transactions, and 1 will be the predicted genuine transactions. Next, we can explore the feature importance of it through the use of Shapley values. Let's run the model through the Shapley explainer function and inspect the feature importance. From the B-swarm plot, it seems to suggest that features V19, V11, V9, and V4 have some explanatory power in detecting anomalies. A lower SHAP value in the aforementioned features has higher feature importance. From our EDA previously, we observed the same for V11 as well, so it can serve as a good reference point. The B-swarm plot provides a view of the global feature importance. But what if we want to see how the model evaluates for a single data point? Let's find out. Let's extract a sample of the index of the data points where it has been marked as fraudulent transactions. Next, we will match the index and see what are the corresponding predictions the model has made for those data points. Take note that the anomaly label is -1 for isolation forest instead of the usual one. We can print out the decision function for those predictions. If the decision function value is negative, it means the model has predicted an anomaly and vice versa. You can see the predicted label matching the decision function values. Next, let's take a look at one of the predicted values and plot a waterfall graph for the contributing features. We can see the actual value is a fraud transaction and the model predicted correctly. From the waterfall graph, we can see that V11 and V14 are the top two features that contributed to the fraud prediction. This is in line with what we observed previously from the EDA. If the features have a negative contributing value, it means that the model is predicting it to be more likely to be anomalous or fraud in this case. You can try on different data points and see what the contributing features are that led to the model predicted value. From the Kaggle dataset, it is recommended to measure the accuracy of the model using the area under the precision recall curve. We will do so by plotting the calculated score via the inverse decision function of the model, and the results are as shown. We can try to train a second model, but this time we will do some feature engineering and modify the input data. We can apply the standard scaler to the amount and include this scaled feature as input for the model to train. We will retain the same hyperparameters as the first model, and see how a change in data input affects the model performance. From the classification report, it seems that the inclusion of the new feature has resulted in a slight dip in model performance for precision and recall. If you have domain knowledge of the problem statement, you can try to use it to do additional feature engineering as data inputs as well. For instance, credit card fraud could occur as a result of enumeration or bin attack, whereby the fraudster attempts to brute force input combination of values and keys to submit transactions to test which cards can be used. In this case, we could do additional risk rank clusters of increased volume of transactions within specific time periods, and if the transactions fall within this, create a feature to rate it as a higher risk, for example. To conclude, isolation forest can be an alternative solution to detecting outliers, especially for those with huge imbalanced dataset problems. Try out different feature engineering inputs for the model and different hyperparameters and see how the model performs. You might be surprised by the results. And that's the end. As always, I will be sharing the link to my notebook in the description section of the video. Do you have any thoughts on it? Feel free to comment in the comment box down below. If you like this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.